Hello, hope you are all well and you are doing great. Today we will continue the simultaneous equation models that we have started in the previous lecture. Let me remind you again, what do we mean by simultaneous equation models? As we said, by simultaneous equation models, we have not just one single equation of regression, but we have simultaneous regression equations, and we have differentiated between the exogenous variables and the endogenous variable. And we said the endogenous variables are the variable that switch its places from being explanatory variable to dependent variable, or from dependent to explanatory variable. Um, and the exogenous variable is the variable that is completely explanatory. So the exogenous variable appears only in the right hand side of the equations, while the endogenous variable appears in both the left hand side and the right hand side of the equations. So in this example, or in this model represented, this is the a simultaneous equation models consisting of m equations. We have m equations represented by m endogenous variable. So y1, y2, y3 till ym are the number of endogenous variables representing the number of equations in the simultaneous equation model. And as you can see, y's, the endogenous variable, are appearing as dependent variable and also as explanatory variables in some other equations. And it consists of k explanatory variables, which are exogenous variables because they appear only in the right hand side of the equations. They are completely exogenous, x1, x2 till xk. So this model is a simultaneous equation model consisting of m equations, or m endogenous variable, and k explanatory variable, or k exogenous variables. So we can say that the variables entering a simultaneous equation models can be classified into two types. The first type is the endogenous variable, and those variables are whose values are determined within the model. The endogenous variable are the variables that switch the places or may appear as explanatory and dependent variable in the same time. So in this example, we have y1 and y2 as endogenous variable, and sometimes we call it determined variable. Why? Because it is determined within the model. The second type is called the predetermined variable, and it's called predetermined because its values, whose values are determined outside the model. And these predetermined variables can be classified into two actually. Exogenous, the predetermined variables, are divided into two categories. Exogenous, current as well as lagged. What do we mean by this? In this example here, we have x1 is an exogenous variable. It is predetermined variable and it's called exogenous variable, and it is current. Why? Because it is collected at the same time point of y. While, for example, we can use x1 t minus 1, which is called a lagged exogenous variable. It's lagged exogenous variable of one time period. I am not collecting it at the current time point, but I am collecting it at the time point minus 1, at the previous time point. It's of one time period, lagged of one time period. And the predetermined variable can be also lagged endogenous. And what do we mean by lagged endogenous? We can use, instead of x1 t minus 1 as explanatory variable, we may use y1 again t minus 1 as explanatory variable. So finally, the predetermined variable are the explanatory variables, the completely explanatory variables. They are explanatory variables completely. They only appear in the right hand side. They are explanatory variables pure. They are predetermined. They are non-stochastic variable. And of course, you remember that the explanatory variables in regression model are non-stochastic. They are non-stochastic variables. And these predetermined can take different form. The first one is completely exogenous at the current time point, like x1 here. Or it could be exogenous also, but at lagged values. At 1 lag, 2 lag, 1 time lag, 2 time lag, whatever. And also, we may use the endogenous variable itself, but lagged. So in this example, I may add another variable, another explanatory variable, which is plus, for example, beta 1, 3, y 1, which is the dependent variable, but at t minus 1. So again, it's an explanatory variable, it's a predetermined variable. So finally, we can conclude that current exogenous or lagged exogenous and lagged endogenous variable are deemed predetermined. Their values are not determined by the model in the current time period. After defining the endogenous and exogenous variable, now we will define what's the structural equation and what are the reduced form equation. Actually, this general form of simultaneous equation models are called structural equation. And also, this example given before is called a structural equation. And actually, from these structural equation or structural form, we can derive what is called the reduced form equation. And by the reduced form equation, we mean a reduced form equation is one that expresses endogenous variable solely in terms of the predetermined variable or exogenous variable and the stochastic disturbances. So it means that in this example, for example, if we have this simultaneous equation model, as we said, this is a structural equation. If I can put y1 as a function in x1 and the disturbance only, and y2 as function in x1 and y2 only, this is called a reduced form equation. Also, from this general example, reduced form equation is the one that expresses the endogenous variable y1, y2, y3 till ym as function solely in the exogenous variable, which are x1 till xk and the disturbances from y1 till ym. So these are structural equations. And from the structural equation, one can solve for the m endogenous variable and derive the reduced form equations. And we will give an example of this, how to do this in the next slide. Now again, back to the Keynesian model of income determination concerning consumption and income. Let me remind you again with the equation we have the consumption represented as function in the income, and we have the income represented as the summation of the consumption plus the investment or the saving. So in this example, we have two structural parameters. We have two structural parameters which are beta naught and beta 1. So now we need to transform this structural form. This of course is a structural form. We need to transform it into a reduced form. How to do this? Again, we need to put the endogenous variable solely in terms of, expressed in terms of the exogenous variable and the disturbances only. So we can say that y equal beta naught plus beta 1y plus u plus I. We have just replaced C in this example by its definition. C equal beta naught plus beta 1y plus u. So finally y equal beta naught plus beta 1y plus u plus I. And then we have y minus beta 1y equal beta naught plus u plus I. And then taking y as a common factor, so we have y multiplied by 1 minus beta 1 equal beta naught plus u plus I. So dividing by 1 minus beta 1, we have y equal beta naught over 1 minus beta 1, I over 1 minus beta 1, u over 1 minus beta 1. And beta naught over 1 minus beta 1 is simply a constant, so we can call it pi 1. And 1 over 1 minus beta 1 again, it's a constant function in the parameter, so we can call it pi 2. So now we have y, which is the endogenous variable, the first endogenous variable, represented as function in y only. Now y is represented as function in I only. So y, the endogenous variable, is represented as function in the exogenous variable and the disturbance only. And again we have another endogenous variable which is C. So by the same way, C equal beta naught plus beta 1 and replace y by its value which is C minus I plus u. So we will have C equal beta naught plus beta 1c plus beta 1i plus u. C minus beta 1c equal beta naught plus beta 1i plus u. And again by taking C as common factor, so we have C multiplied by 1 minus beta 1 equal beta naught plus beta 1i. And dividing by 1 minus beta 1, so we have finally C equal beta naught over 1 minus beta 1, beta 1 over 1 minus beta 1i, and u over 1 minus beta 1. As if now, instead of beta naught over 1 minus beta 1, it's pi 3. And beta 1 over 1 minus beta 1, let's call it pi 4. And the new disturbance term, which is u over 1 minus beta 1, exactly like in the equation number 1, let us call it w. So now, instead of having structural equation, which are equations that we have endogenous variable represented as function in endogenous and exogenous, both of them, now we have two equations. We have these two equations, this one and this one. These two equations are called the reduced form equations. Why? Because the endogenous variables y and c are represented in the exogenous variable I and the disturbances only. There is no endogenous variable appearing in the right hand side. There is no endogenous variable appearing as explanatory variable. So now we have, as we said, two structural parameters which are beta naught and beta 1, and we have how many reduced form parameters? Reduced parameter, we have pi 1, pi 2, and pi 3, and pi 4. So we have transformed two structural equations with two structural parameters into two reduced form equations with four reduced parameters. Now we know what do we mean by endogenous variable, exogenous variable, structural equation, and reduced form equation. Now the question is how to fit simultaneous equation models. Actually, let me remind you again that we cannot apply the OLS to fit each equation separately. Why? Because the exogenous variable, the explanatory variable, and the disturbance term are correlated. They are not independent anymore. So one of the important assumptions of the OLS is violated. That's why we cannot apply the OLS in order to fit simultaneous equation model. Instead, we have to use what's called the indirect least squares. And actually, the indirect least squares is based on deriving the reduced form equations from the structural form equation. So back to the example of consumption, let me remind you again with the two equations. These two equations here are the reduced form equations derived before, and they are reduced. Why? Because the endogenous variable y and c are represented in terms of the exogenous variable I and the disturbances only. There are no endogenous variables represented as explanatory variables. And since I here, this explanatory variable here is non-stochastic, and of course it's assumed that it's uncorrelated with the error term. So in these two equations, the explanatory variable and the error term are not correlated. So the assumption of the OLS is now satisfied. We have two equations where the explanatory variable, the non-stochastic variable, and the disturbance are not correlated. So we can simply take each equation and fit it using OLS method. But in this case, we are not estimating the original structural equation. We are not obtaining beta naught and beta 1, but instead we are obtaining pi 1, pi 2, pi 3, pi 4. But as we said, pi 1 is simply a function in beta naught and beta 1. And again, beta 2 is function in beta 1, pi 3 is function in beta naught and beta 1, and pi 4 is function in beta 1. So we can solve these equations simultaneously to find the values of beta naught and beta 1. So let me summarize to you the steps that should be followed in order to apply the indirect least squares. First of all, you have to transform the structural equation of simultaneous equation models into reduced form equation, into equations where the endogenous variable are represented in terms of the exogenous variable only and the disturbances. And in this case, the assumptions of the OLS is satisfied. So moving to the second step, you have to just apply the OLS in each equation. You can apply the OLS to each equation of these, and from the OLS you will find the estimated values for the reduced form parameters, which are pi 1, pi 2, pi 3, and pi 4. And then finally, from these values you can solve the equations and find the values of beta naught and beta 1, which are the structural parameters. Identification. Actually, identification is a very important concept in simultaneous equation models. And by the identification problem, we mean whether numerical estimates of the parameters of a structural equation can be obtained from the estimated reduced form coefficients. Let me remind you again with the steps of the indirect least squares? We said we start by obtaining the reduced form equation from the structural equation. And then, since the assumption of the OLS is satisfied in the reduced form, so we can simply estimate the reduced form using the OLS. And finally, we can use the estimated values or the estimated parameters of the reduced form to find the estimated values of the parameters in the structural form. But actually, sometimes we cannot do this. We cannot find or solve the values of the structural parameters from the reduced form parameters. We cannot do the last step of the indirect least square, which is finding the values of the structural parameters from the values of the reduced form parameters. So let me remind you again with the example of consumption. Again, we have the following two equations. From these two equations, of course, are structural equations. In order to apply the ILS or the indirect least square, or to estimate beta naught and beta 1, first we will derive the reduced form, which are given by these two equations. And then, since the assumptions are satisfied, so we can apply the OLS to obtain the reduced form parameters pi 1, pi 2, pi 3, and pi 4. And then, from these functions, from these equations, from these four equations, pi 1 equals beta naught over 1 minus beta 1, and so on, we can solve these equations together in order to find the values of beta naught and beta 1 from pi 1, pi 2, pi 3, pi 4. But actually, in some situations, we cannot solve this. We cannot obtain the estimated values of the structural parameters from the estimated values of the reduced parameters, unless the function or the equation is identified. If the equation is identified, in this case we can do the last step, which is deriving the structural parameters from the reduced parameters. But if the equation is unidentified or not identified, in this case we will not be able to find the estimated values of the structural parameters from the reduced parameters. But how to know whether the equation or whether this simultaneous equation model is identified or not? Actually, there is a rule to do this by comparing the number of parameters in the reduced form and the number of parameters in the structural form. If the number of parameters in the reduced form is exactly equal to the number of parameters in the structural form, in this case it is exactly or just identified equation, and in this case we can obtain the estimated parameters, the estimated structural parameters from the reduced parameters. If number of parameters reduced is greater than the number of parameters structured, in this case it's over identified, and again we can obtain estimates for the parameter. But if the number of parameters in the reduced form is less than the number of parameters in the structure form, in this case it's unidentified or under-identified. In other words, I cannot obtain the estimated structural coefficients from the reduced coefficients. I cannot obtain beta naught and beta 1 from pi 1, pi 2, pi 3, and pi 4. So let us apply this rule to this example. In this case, we have how many structural parameters? We have ns, n structure, equal to, we have only beta naught and beta 1. And we have how many reduced parameters? We have 4, pi 1, pi 2, pi 3, and pi 4. So in this case, N4 is greater than NS. So in this case, we are over-identified, which means we can obtain solution for beta naught, numerical estimate for beta naught and beta 1 from pi 1, pi 2, pi 3, and pi 4. But actually, this rule or this approach has a disadvantage, which is
in order to know whether I can do this last step, whether I can obtain the structural parameters from the reduced parameter or not, I have to go through all the steps for finding the reduced form. I have to transform from structural to reduced form in order to know how many reduced parameters I have, and then compare the number of reduced parameter with the number of structural parameter. So sometimes I will go through all the steps and I will find the reduced form equation, and then I will figure out that I cannot solve it. I cannot find the structural parameter from the reduced parameter, as if I have wasted my time going through all these steps in order to find the reduced form parameters. So there is another approach, or there is another rule that can be used in order to check the identification of the simultaneous equations without obtaining the reduced form equation.
Okay, now we have an assignment. For the following simultaneous equation model, derive the reduced form and check the identification. If you have these two simultaneous equation model, and actually let me remind you the main concept. How many endogenous variables do we have here? How many endogenous? And again, the endogenous variables are the variable that may appear on the left hand side and on the right hand side. The variables that switch their places from being dependent to explanatory, or explanatory to be dependent variable. So how many endogenous variables here? Yes, we have two endogenous variables, which are y1 and y2. So in order to derive the reduced form equation, you will put each one of these endogenous variables in function that includes only the exogenous variable and the error term. So what is the exogenous variable? Again, the exogenous variable is the variable that appears only in the right hand side. It's explanatory completely. It's non-stochastic. So how many exogenous variable here? We have x1 and x2. So we have two endogenous variable and two exogenous variable, x1 and x2. So the reduced form equation, we will derive two reduced form equation, one for y1 and the other one for y2, where in each one the function include only x's, x1 and x2, and an error term only, and the same for y2. It includes only x's and error term. So you will put y1 and y2 in function including only the exogenous variable x1 and x2 and the error term. And this will be your reduced form equation. And then you will check your identification. How? By comparing the number of parameters in the structural form with the number of parameters in the reduced form. So this is the structural form. So how many parameters do we have? We have beta naught, beta 1, beta 2, alpha naught, alpha 1, and alpha 2. So we have 6 structural parameters needed to be estimated. We need to estimate 6 structural parameters. So, of course, in order to be able to find the structural parameters from the reduced parameters, the number of reduced parameters should be at least equal, which means greater than or equal, the number of structural parameters. So after obtaining the reduced form equation, you will see how many parameters do we have. If the number of parameters is equal 6 exactly, so it's exactly identified or just identified. So in this case, you can obtain the structural parameter from the reduced parameter. But if the number of parameters in the reduced form is greater than, again it's over identified, and again you can solve it and obtain the structural parameter from the reduced one. But only if the number of reduced parameters is less than 6, in this case only, you will not be able to find the
structural parameter from the reduced form parameter. So you will do it by yourself, you will check this condition by yourself. I just want to be sure that you can understand what is the meaning of these concepts, because it's very important, the concept of endogenous, exogenous, structural equation, reduced equation, identification, actually I will upload on Moodle the model answer for this assignment. And please do not waste your time in writing on Word. Do not type on a computer. You can just handwrite it, and you can take a photo by mobile and send it to me by email. Please do not waste your time writing this on a computer. Just handwrite and take a photo by mobile and send it to me. Finally, thank you all so much, and as I said, I will upload the model answer for this assignment. And in the next lecture we will start talking about the two conditions, the order condition and the rank condition, that can be used to check the identification of the simultaneous equation model. Thank you all.